So dear students, now we will move on to the last session, our theoretical session with respect to structure of an atom. So previously we have described what the quantum numbers are and what are the various individual significance of the four different quantum numbers called as principal, azimuthal, magnetic, and then the spin quantum numbers. So usually the principal quantum number signifies the first main shell, or indirectly called as orbit. Then what is the size of that? What is the distance from the nucleus to the electron in the given orbit? What is the energy related to that? Then how many electrons that has been accommodated, which is given by the formula 2n square. The second one is azimuthal, called subsidiary or angular quantum number, which will describe first what is the name of the subshell in the given main shell. Then what is the shape of that particular subshell? It also gives the angular momentum of the orbital angular momentum of that one, which is given by the formula root of L into L plus 1 divided by 2 into H divided by 2 pi. H into H by 2 pi. Okay. Then it gives the total number of values for L are just only n. Means L can have totally how many values? N values. The values of L are, it starts from 0, 1, 2, 3, so on up to the last one is n minus 1. If L is equal to 0, it is called as S subshell having a spherical shape. L is equal to 1, we can have the P subshell having the dumbbell shape. L is equal to 2, it is called as a D subshell, which is having a double dumbbell shape. L is equal to 3, we are having the F subshell called as having a complex or complicated shapes. So that is the second quantum number called as azimuthal. The third is the magnetic, or it is also called as a orientation quantum number. What it signifies here? First, it signifies what is the name of the orbital, or what the orbital. It gives the orbital present in the given subshell. As it gives the orbital means, the second thing is it gives the exact direction, or it is also called as orientation of that particular orbital in the given subshell. Then it gives the magnetic momentum of the revolving electron in the given orbital. Then M can have totally the 2L plus 1 values. M has how many values? 2L plus 1 values. Those values are the values of M are, it starts from minus L, so on up to the middle is 0, and so on up to the last one is plus L. Means it varies from minus L to plus L through the 0. So that gives the number of orbitals that has been present. And finally, what is the last? The spin quantum number. What it signifies? It signifies the spinning of an electron on its own axis in the given orbital. That is, it has given the two different directions. Means, it gives the direction of spinning of an orbital in the given direction of spinning of an electron on its own axis in the given orbital. That is, S can have the two possibilities, only two values. What are those? Plus half and then the minus half. Plus half refers to the clockwise spin and the minus half refers to the which one? Anti-clockwise spin. So that is about the fourth quantum number called as the spin quantum number. So by knowing all the four set numbers, we will designate what is the exact state or address of or state of an electron around the nucleus of the atom. So that is the main significance with respect to what numbers? The quantum numbers. Okay. So now, what is electronic configuration? What is which one? Electronic configuration. Configuration means what? Arrangement or accommodation or accumulation. It is the process of arrangement. It's the process of which one? Arrangement, which is also called as accommodation. Accommodation, or sometimes it is also called as accumulation. Process of which one? Arrangement or accommodation or accumulation of electrons in various atomic orbitals. Which orbitals here? They are now called as the atomic orbitals. In various atomic orbitals around the nucleus of the given atom, that refers to which one? The electronic configuration. accommodation. This is the definition. It's a process of what? Accommodation of various, or accommodation or arrangement or accumulation of which one? The electrons around, or first where they can be accommodated in the various atomic orbitals around the which one? The nucleus of the given atom. So now, rules are principles for EC, electronic configuration of elements. How to have the which one? The rules, or what are the various rules, or it may be the principles that has been fit for the electronic configuration for the various elements. The first one is Aufbau principle. It's called as what? Aufbau principle. Here, Aufbau means it is having a meaning of to build up. The meaning of Aufbau, a Latin term relative to the which one? Building up. Means how to build up. Means how to build up means how to arrange the various electrons around the nucleus of an atom in the various atomic orbitals, that is given by the first principle called as Aufbau principle. So what is the statement here? Statement. Electrons enters into the various atomic orbitals in the increasing order of their respective energies. This is a statement. What is the statement for Aufbau principle here? It is the electrons enters into the various atomic orbitals, because electrons can be accommodated in the various atomic orbitals. How they are arranged? They are entering into the various atomic orbitals always in the increasing order of their which one? Energies. Means, first some electrons enters into the lower energy atomic orbitals, then to higher energy atomic orbitals, and so on. Means the electrons has to be first enter into the what? Lower energy atomic orbitals. After the filling of those electrons, next we will move on to the higher energy atomic orbitals. Then we will move on to the further higher energy atomic orbitals. So that is a statement according to the what principle? The above principles. Means the electrons enters into the various atomic orbitals always in the increasing order of their which one? Respective energies. Means the electrons first enters into the lower energy atomic orbitals, then to the higher energy, and still to the higher energy atomic orbitals. So this is obtained by knowing AOELD. AOELD, that is atomic orbital energy level diagram. The diagram is also called as what? AOELD, that is called atomic orbital energy level diagram. So as if we know that first, it has to be very clear. N is equal to 1 means how many subshells we are having? 1s is subshell. 1s has how many orbital? 1 orbital. N is equal to 2 means we are having the 2 subshells in the form of 2s and then the 2p. N is equal to 3 means it is 3s and then the 3p and then the 3d. N is equal to 4 means it is 4s, 4p, 4d and then 4f. N is equal to 5 means it is called 5s, 5p, 5d, 5f and then 5g and so on. Means, I have mentioned one formula for that. If n is the principal quantum number, what number it is? Principal quantum number. Then the number of main shells or orbits is also equal to n. The number of subshells is also equal to n. The number of orbitals is given by n square, and the number of electrons is given by 2 into n square. N is the number of main shell, n is the number of subshells, n square is the number of orbitals, and 2n square is the number of which one? Electrons. So here 1 means 1 subshell, 2 means 2 subshells, 3 means 3 subshells, 4 means 4 subshells, 5 means 5 subshells. So that is the general concept with respect to the value of n. N is called as a principal quantum number, or indirectly it is called as an orbit number. Okay. So let us have the energy level diagram with respect to that. This is now the energy axis. What axis here? Energy axis. This is lower energy is 1s. First orbit has only one shell, subshell, that is called as 1s. Then we are having the second one that is called as 2s along with 2p. 2s along with 2p. Third orbit has 3s, 3p, and then the 3d. 4 has 4s, 4p, 4s, 4p, 4d, and then 4f. 5 has 5s, 5p, 5d, and then 5f. Actually, we are having another one that is called as 5g. But as for now, the 118 elements or the 100 electrons has been accommodated, means there is no g subshell up to the F, that is called as 5 is sufficient. Similarly, 6 has actually 6, but here we are having only the 3 for that, that is 6s, 6p, and then the 6d. Then 7s followed by 7. Okay, so this is the energy distribution, or indirectly it is called as the energy level diagram. Means how to fill up the electrons now. First you have to be very clear. S can accommodate 2 electrons, P can accommodate 6 electrons, D can accommodate 10 electrons, and F can accommodate 14 electrons. Because S has only one subshell or one orbital. Orbital can accommodate how many electrons? 2 electrons. P has how many suborbitals? P subshell has 3 orbitals. What are those? Px, Py, and Pz. Means how many electrons totally? 3 2s are, that is equal to 6. D has 5 orbitals. D subshell has 5 orbitals. What are those? dxy, dyz, dxzx, dx square y square, and dz square. Each can accommodate how many electrons? 2. 2 into 5, that is equal to 10. Similarly, F has 7 orbitals. Each orbital has 2. Therefore, total electrons in the F subshell is totally the 14. Means it has to be very clear. First, S can accommodate 2 electrons. P can accommodate 6. D can accommodate 10, and F can accommodate 14. So this you have to be very familiar first. Okay. Next, how to write the energy level diagram with respect to this here. So here, the arrow mark is very important here. This arrow mark is very important here. So I will just rub out this. Okay. So this is now the AOELD. The lowest that has been first entered from the lower level, the first that has to be entered is 1s. 1s means don't come here, we have to be at the bottom again. Then we are having the 2s. Don't enter here like this, we have to enter from the bottom. After 2s, again we have to move from this lower level, 2p followed by 3s. After 3s, it is now 3p, then 4s. 4s after again it is 3d, 4p, 5s, then 4d, 5p, 6s, 4f, 6t, 5d, 6p, 7s, and then 5f, 6d, and then this one. Means the symbolic representation, that is a diacritic representation. Symbolic representation of AOELD is, that's a diacritic representation, but here it is a symbolic representation. First, 1s is less than, after 1s we are having the what? 2s. After 2s we will have the 2p, then 3s. After 3s we are having the 3p. After 3p we are having 4s. 4s after we are having the 3d. After 3d, 4s after 3d, now we are having the 4p. 4p followed by the 5s. 5s after we are having the 4d. 4d after we are having the 5p. 5p after we are having the 6s. 6s means after that 4f. 4f means after we are having the 5d. 5d after we are having the 6p. 6p after we are having 7s. 7s after 7s we are having the which one? 5f. After 5f we are having the 6d. 6d after we are having the 7, and so on. Here the first 2 electrons enters into which orbital? 1s orbital. Why? Because S can accommodate how many electrons? Only 2 electrons. Means the first 2 electrons always enters into the which orbital? It is a 1s. Next, the next 2 electrons enters into 2s orbital, because again it is what? 2s. Then 2p can accommodate. 2p has first how many orbitals? 3 orbitals. What are those? 2px, 2py, and 2pz. Each can accommodate how many electrons? 2 electrons. 2 3s are 6. Means the next 6 electrons enters into which orbitals? 2p orbitals. So here we are having the 2p orbitals as what? 2px, 2py, and then the 2pz. Each can accommodate how many electrons? 2 electrons. Then the next 2 electrons can accommodate in the 3s orbitals, and so on. After 3s we are having the 3p. 3p can accommodate how many electrons? 6 electrons. Then having the 2 electrons for 4s. Then 3d can accommodate how many electrons? 10 electrons. Means how to arrange here? Just we have to arrange those electrons in the increasing order of their which one? Energies, and that particular statement is called as what principle? Aufbau principle. What's the statement here? Electrons always enters into the which orbitals? Atomic orbitals. How? In the increasing order of their energies. Means first the electrons enters into the lower energy orbitals, then we are having the higher energy orbitals, then we are having the further higher energy atomic orbitals. Then how to know the energy of those atomic orbitals? Which is done by a diagram, and that diagram is called as atomic orbital energy level diagram. Atomic orbital energy level diagram. For that you have to be very familiar with respect to the subshells and their respective orbitals. N is equal to first orbit has only one subshell called as 1s. 2 can have 2 orbitals called as 2s and 2p. 3 can have 3s, 3p, 3d. 4 can have 4s, 4p, 4d, and then 4f. 5 can have actually the 5s, 5p, 5d, 5f, and then 5g. But as per the 118 elements of the electrons is concerned, we are having up to only the 5f. Then for 6 we are having only 3, that is 6s, 6p, 6d, and then we are having the 2 for 7s and 7p. Just always move from the bottom to the upwards. Bottom to the upwards. For every time we have to drop to the bottom and then move to the higher level. On that basis we are getting the symbolic representation of which one? AOELD. What is that AOELD? It is called atomic orbital energy level diagram. So that is the first principle called as the Aufbau principle, that is called as the electrons always enters into the various atomic orbitals, always in the increasing order of their which one? Energies. Okay. Next, the second rule or the principle relative to this electronic configuration is the Pauli's exclusion principle. What's that? Pauli's exclusion principle. The second principle is, or the rules is, Pauli's exclusion principle. Pauli's exclusion principle. So let's have the statement first. What it states. No two electrons in an atom, no two electrons in an atom can have the same set of Q numbers. What's Q numbers? Quantum numbers. If I choose an atom, if I choose how many electrons? 2 electrons. That doesn't have the same set of what numbers? Quantum numbers. That is, no two electrons in the given atom cannot have, or no means it is can. Here if I just only mention 2 electrons means it is cannot. Means no two electrons in an atom can have the same set of what numbers? Quantum numbers. Or we can have the another statement. Any two electrons, any two which one? Electrons in an atom cannot have the same set of what numbers? Quantum numbers. This is also right. If I initially mention no means it is can have the same set of quantum numbers. Or if I do not mention no means any two electrons in an atom cannot have the what? Same set of what numbers? Quantum numbers. Or indirectly, any AO is called as what? Atomic orbital, can accommodate only 2 electrons with always the opposite spins. Opposite spins. Any atomic orbital can accommodate how much? Only the 2 electrons with what spins? The opposite spins. Means if one is moving in the clockwise, then the another must compulsory move in the what? Anti-clockwise. That is, we should have the opposite spins. Okay. So let's have the illustration with respect to this. Consider the 2 electrons. Consider the helium atom with Z is equal to 2. Z is atomic number 2. Why I can't take the hydrogen means the first element is actually the hydrogen, but we can't take the hydrogen. Why? Because it contains only 1 electron. Means we have to start at least with what? The 2, that is in the form of helium. Electronic configuration of helium is with Z is equal to 2 is 1s2. Because the first orbital having the lower energy is what? 1s. After that we are having the 2s. Then we are having the 2p. Then 3s, 3p and so on. Okay. The first is 1s2. For first electron, what's the first electron here? 1s1. What is N? What is L? What is M? And what is S? What is N, L, M, S? They are the set of quantum numbers. N is equal to 1 means it is the first main shell. Principal quantum number. L is referring to the azimuthal quantum number. M is referring to the magnetic quantum number. And S refers to the spin quantum number. As it is a first, 1s1 means it is a first orbit, n is equal to 1. N is equal to what? 1. As it is a s subshell means C. For s subshell, what is L? L is always equal to what? 0. L is equal to what? 0. If L is equal to 0 means M is always equal to 0 because the values of M are minus L2 plus L through the 0. Minus 0 plus 0 means it is nothing but 0. M is also equal to 0. As it is a first electron means usually we are preferring the given the direction in the form of clockwise. Clockwise is nothing but plus half. So what is 1, 0, 0 plus half means? It is the set of 4 quantum numbers for the which electron? First electron in the which atom? The helium atom. Let us take the second one. For second electron, let us take the chance. The second electron is actually the what? 1s2. What's that? 1s2. Again 1s2 means the first quantum number is, principal quantum number is 1. Again s subshell means L is equal to what? 0. If L is equal to 0 means M is always equal to 0. But it is a second electron or a first electron here. 1s1 is a first electron, 1s2 means it is a second electron. First electron is already moving in the clockwise direction means what is the second electron must move in the anti-clockwise. Anti-clockwise means it is having means. So this is a set of electrons, quantum numbers for the first electron, and this is a set of 4 quantum numbers for the second electron. But whether the set of 4 quantum numbers for the 2 electrons in the helium atom is same or different here? N is equal, L is equal, M is also equal, but there is a change in the value of S. Means they cannot have the same set of what numbers? Quantum numbers. Or indirectly what we can mention? Any atomic orbital is having the capacity of accommodating how many electrons? Only 2 electrons with what spins? Opposite spins. Means the first electron, suppose if it is moving the clockwise, means the second must be always in the anti-clockwise. So that is the statement called as what principle? Pauli's exclusion principle. What is that Pauli's exclusion principle here? We can have the 3 different statements. What is the first one? No 2 electrons in an atom can have the same set of what numbers? Quantum numbers. Are any 2 electrons in the given atom cannot have the same set of what numbers? Quantum numbers. Or indirectly, any atomic orbitals always accommodate how many electrons? Only the 2 electrons with what spins? Opposite spins. Okay, so we have taken the very simplest example in the form of which one? Helium. Not only take that helium as a best example, you can choose any one. Just consider how many electrons? 2 electrons. Okay, so let us have the next in the form of the third rules, or it may be the principle for the electronic configuration. The third rule or principle for that one is let's have the third one in the form of Hund's rule. Hund's rule of maximum multiplicity. Maximum multiplicity. So let's have the statement related to that. Electron pairing in PR, DR, F orbitals of same energies takes place if and only if and only if each atomic orbital is or gets half filled, or sometimes it is also called as singly filled. Means we are not considering on the yes. Why? Because S can have only the 2 electrons. Suppose if one is in the clockwise, then that must be in the anti-clockwise. There is no chance for that. Suppose if it is of P, we are having the 3 called as Px, Py and then the Pz. If I take D, we are having the dxy, dyz, dzx, x square y square and dz square. Means we are having at least 2 or more orbitals. But all these will have the what energy? Same energy. This set is also having the what energy? Same energy. Means in case of what orbitals here? Either the p or the d or the f orbitals. Electron pairing takes place of, in case of the same energy orbitals, if and only what? Each atomic orbitals is what? Filled. Half filled. Half filled is also called as singly filled. Okay. So let us have the illustration related to this. Illustration. Consider the element oxygen with atomic number is equal to 8. What's the atomic number of this one? It is 8. What is the EC of O? Z is equal to 8. First you have to be very familiar. What is that? 1s less than, 2s less than, 2p less than, 3s less than, 3p less than, 4s less than, 3d less than and so on. This is the symbolic representation of what? AOE. First we will have the 1s. S can accommodate how many electrons? 2 electrons. It is 1s2. After filling of 1s we are having the 2s. Therefore 2s. S is also having again 2. 1s2, 2s2. P can accommodate how many electrons? 6 electrons. Therefore it is 2p. But only we are having the 8 electrons. That among the 8 electrons, 2 has been filled in 1s, 2 has been filled in the 2s, and now I left with only the 4. So this is what this is? The electronic configuration with respect to which one? The oxygen atom having an atomic number of what? 8. That is 1s2, 2s2, 2p4. So here the first possibility is, this I can represent in the form 2 types. S is having only 1 orbital, 2s is also 1 orbital, and 2p is having 3 orbitals. This is 1s, 2s, 2px, 2py and then the 2pz. There is another chance, or we can take another representation with respect to that. 1s, 2s, 2px, 2py, 2pz. Okay? Let us have the arrangement. SC is having only 1 orbital, it can accommodate only 2 electrons. If one is in the clockwise, then the another must be in the anti-clockwise. The first 2 electrons, 1s1 and then 1s2. Why I am writing that in the opposite way for the arrow marks? That shows that the first is moving in the clockwise and the second is moving in the anti-clockwise. This is clockwise and this is anti-clockwise. That is the difference in the representation of arrangement of electrons either in the clockwise spin or it may be the anti-clockwise. Then we are having the 2s2, 2s1 and 2s2. One is clockwise, another is a what? Anti-clockwise. In 2p we are having the 3 orbitals called as 2px, 2py and then the 2pz. 2s, 2p2 here. Then we are having the 2p2 here. Now it is a complete. This is one possibility. We can have the second one also. Again it is 1s2, 2s2. With respect to s there is no problem here. But with respect to 2p we are having the 3 chances called as 2px, 2py and then 2pz. Let us give 1 electron each for this. 2px1, 2py1 and then 2pz1. Means 2px, 2py, 2pz all will have the same energy. For the same energy orbitals, each orbitals has to be first what filled? Half filled. It is also called as singly filled. Means I am distributing the 3 electrons in such a way that each orbital gets how many electrons? 1 electrons. So now it becomes actually the 7. Then how to pair that? After this it start to get pair. It is called as electron pairing. Electron pairing in case of the p or the d or the f orbitals of what energy? Preferably the same energy takes place if and only if each atomic orbital is what filled? Half filled. Half filled is also called as singly filled. So therefore, among those two, this is not the and this is correct. Why? Because in case of 2p4 directly, sorry, in case of 2px it directly gets paired. It directly gets paired, but there is no electron in case of the which one? 2pz. Therefore, this is 100% wrong here. Means how we have to fill? In case of the orbitals having the same energy, what we have to do? First we have to give 1 electrons each. It is called as what filled? Singly filled, or it is also called as what filled? Half filled. After the half filled is complete in each of the atomic orbitals having the what energy? Same energy. Then it starts to get pairing. That is called as electron pairing in case of either the p or the d or the f orbitals of what energy? Same energy takes place if and only if each atomic orbitals is what filled? Half filled. Half filled is also called as what filled? The singly filled. Then 4, according to Hund's rule of maximum multiplicity, the electronic configuration, the second is going to be correct compared to that of which one? First. Means we can't write this is while it is. Because we have to give the each electrons for the same energy atomic orbital such that each are what filled? Half filled called as singly filled, and then you have to start with the pairing. So that rule is called as Hund's rule of what? Maximum multiplicity. Okay. So let us have the next one, the fourth one. The fourth rule or principle. The fourth one is N plus L rule, which is also called as Bohr-Bury's rule. N plus L rule is also called as what? Bohr-Bury's rule. So as for this, we are having the two different statements. Statement 1. And AO, what is AO here? Atomic orbital. Atomic orbital. Among, let us take first. Among two orbitals, AOs, let us take. Among two atomic orbitals, an AO atomic orbital having higher value of N plus L has higher energy and vice versa. Means if I consider how much at least? 2 atomic orbitals. Among those 2 atomic orbitals, any atomic orbital having the higher N plus L value, it must have the higher energy, or it may be the vice versa. We can have the statement 2 also. Statement 2, because we are having the 2 statements related to this. Among the 2 AOs, atomic orbitals, having same N plus L value, same what? N plus L value, and AO having higher value of N has higher energy and vice versa. Vice versa. So here it is very clear, just on the values of which one? N plus L. Suppose if I consider any two atomic orbitals and those two atomic orbitals among that, any atomic orbital having the higher value of N plus L will have the higher energy. Suppose if the two atomic orbitals is having the same N plus L value, then we have to consider the higher value of N will have the which energy? Higher energy. Okay? Let us consider our illustration. Consider two AOs, namely 3s and 4p orbitals. We are considering the two orbitals. What are those? 3s and 4p. For 3s orbital, for which orbital? 3s orbital. What is N? As it is a third orbit means N is equal to 3 here. As it is a S subshell means L is equal to 0 here. Therefore, what is N plus L? It's equal to 3. For which orbital? First I am expressing here the 3s orbital, N is equal to 3 and S subshell means L is equal to 0. Therefore, what is N plus L? It's equal to 3. For suppose if it is 4p orbital, which orbital? 4p orbital. N is equal to 4th orbit means N is equal to 4. P subshell means L is equal to 1. L is equal to 0, S subshell, L is equal to 1, P subshell, L is equal to 2, D subshell, L is equal to 3, F subshell. As it is P subshell means L is equal to 1, therefore, what is N plus? It is equal to 5. Therefore, which is having the higher energy here? Or higher N plus L value? Higher N plus L value is in case of 4p. Therefore, 4p has higher N plus L value, hence higher energy. Therefore, 4p is greater than 3s. Which orbital is having which energy? 4p is having the higher energy compared to that of which one? The 3s. Let us consider second illustration. Consider two AOs, 4s and 3p. Now we are considering the two. What are those? 4s and 3p. For 4s orbital, for which orbital? 4s orbital. What is N? 4. S subshell means L is equal to 0. L is equal to 0. Therefore, what is N plus L? 4 plus 0, that is equal to 4. Let us take another one that is called as 3p orbital. 3p orbital means N is equal to 3 here. P subshell means L is equal to 1. P subshell means L is equal to 1. L is equal to 1 means N plus L is equal to 4. Now I enter into the second statement. What's that? Among the two atomic orbitals having the same N plus L value, in both the cases, what is the N plus L value? Same, that is 4. Then which is having the higher energy? Then an atomic orbital having the higher value of which one? N. Higher value of what? N. That is having the highest energy. As both will have the same energy here. But which is having the highest value of energy for that? It is this. As 4s has higher value of N, it has more energy. Therefore, 4s is greater than which one? 4s is greater than what? 3p. This rule is called as what? N plus L rule, which is also called as Bohr-Buriess rule. Bohr-Buriess rule is having two different statements. What is that? Suppose if I consider how many atomic orbitals? 2 atomic orbitals, then an atomic orbitals will be having the what? Higher N plus L value is having the higher energy, or it may be the vice versa. Suppose if I consider the same 2 atomic orbitals are the 2 atomic orbitals, but both have the same what values? N plus L values. Then what we have to consider? Instead of N plus L, what we have to consider here? An atomic orbital having the higher value of N will have the higher energy, or it may be the vice versa. This statement is called as the N plus L rule, which is also called as what? The Bohr-Bury rule. Okay. So next we left with the last one, that is called as the last rule. The fifth one is rule of principle of stability of an atom. Stability of an atom. An atom with either completely filled or half filled configuration. Any atom, or it may be the which one? Element, which is having either a what filled? A completely filled, or it may be the half filled configuration, leads to an extra stability to that atom. To that atom. So let us take the illustration or consider fluorine and then neon. Fluorine Z is 9, this is 10. Fluorine atomic number is what? 9, and the neon atomic number is 10. It's having a configuration of 1s2 first, 2s2 next, and then 2p5. This is 1s2, 2s2, 2p6. 1s2, 2s2, 2p6. Or if I extend this as, means by this configuration we have to mention which is the most stable here. 1s2 means as usual 1s2, 2s2 means it is having a 2s2, but 2p is having the 3 orbitals. What are those? 2px, 2py, and then the 2pz. Apply the Hund's rule. In case of the electron pairing of the energy of the same atomic orbitals, each orbital is first what filled? Half filled. Then it starts to get paired. So 1s2, 2s2 means 4 here, but actually we are having a 9 here. 1, 1, 1. So totally 4 plus 3, that is equal to 7. Then starts pairing here. 2, 2, 1. Suppose in case of this one it is 1s2, 2s2, 2px, 2py, and then 2pz. 1, 1, 1 first, then we are having the 2, 2, 2 here. So this is having a set of completely filled, but this is having a set of 2 are completely filled and 1 is, because we don't consider the previous, because they are innermost. As this is having a set of completely filled means it is found to be the more stable, and this is found to be the less stable. Means why the neon get the extra stability here? Because it is having a set of what filled? Completely filled. Similarly, consider carbon, nitrogen, and then oxygen. Carbon, nitrogen, oxygen. Z is equal to 6, I think. Z is equal to 7, and Z is equal to 8. I will write that as 1s2, 2s2, 2p2. I will write this as 1s2, 2s2, 2p3. I will write this as 1s2, 2s2, 2p4. 2p4. Split that out. 1s2, 2s2, 2px, 2py, 2pz. 1s2, 2s2, 2px, 2py, 2pz. In case of this one again, 1s2, 2s2, 2px, 2py, and then 2pz. In the first cases, no problem here. 1s2, 2s2, 1s2, 2s2, 1s2, 2s2 is common. Next, how many electrons we left here? 2. According to Hund's rule, I have to mention 1, 1 here it is 0. 1 1 0, because we are having only the 2 electrons in the 2p right now. But in case of we are having a 3 here, therefore we can have 1 1 1 1 1 1. In case of 2p4, it is again 1 1 1. I left with another one, therefore it is 2 1 1. So therefore among carbon, nitrogen and oxygen, which is found to be the more stable here. So this is found to be the more stable compared to the top, either the carbon or it may be the oxygen. Why? Because this is having a set of what filled? Half filled. Half filled is now also considered to be the what stable? More stable. Means which filled configurations? Means any element or it may be the atom which is having either a set of what filled? First, a completely filled, or it may be the half filled configurations, always leads to the what stability? Extra stability for that particular atom under consideration. So among therefore carbon, oxygen and then nitrogen. Nitrogen is found to be the relatively more stable element because it is having the set of what filled half orbitals? P orbitals, 2p orbitals. In case of fluorine and then the neon, which is having the highest stability, it is the neon is having the highest stability because it is having a set of completely filled. Therefore, any atom or the element which is having a set, first watch, the completely filled set will have the highest stability compared to that of the which one? The half filled orbitals. Okay. So these are the 5 different rules to have the electronic configuration of elements. That is, first one is Aufbau principle, the second one is Pauli's exclusion principle, the third one is called as Hund's rule of maximum multiplicity, the fourth one is called as N plus L rule, which is also called as Bohr-Burridge rule, and finally the rule or principle with respect to the stability of an atom. Okay. So this is about the electronic configuration and what are the various rules or the principles related to the electronic configuration. Now, you have to be very familiar, or you have to write the electronic configuration of all the elements from Z is equal to 1 to Z is equal to 54. So it is the work of yours right now. Work of yours, because you should be very familiar first. The first is what? 1s less than 2s less than 2p less than 3s less than 3p less than 4s less than 3d less than 4p and so on. So here we know that it can accommodate 2 here, it can accommodate 2 here, p can accommodate 6 here, s can accommodate 2 here, p can accommodate 6 here, 2, 10, then we are having the 6 up to this I think. 10, 20, 30, 36. After 4p we will have the 5s, and then the after 5s we are having the 4d. 4d after we are having the 4p. This is 2 I think, this is 10 I think, this is 6 I think. Sorry, I have done one mistake here. 4p, here it is 5p, sorry, it is 5p. So up to this it is 36 I think, 36, 36, 38, 48, 48 plus 6, that is equal to 54. Means up to what? 54. Means the maximum that you can achieve for this one is going to be the 5p orbitals. You have to be very familiar. S can accommodate only 2, P can accommodate the 6, D can accommodate 10 electrons, whereas the F can accommodate the 14 electrons. But as far this is concerned, we didn't have any only the we didn't have the F subshells or the F orbitals. Only into the D orbitals we can have that. Okay. So it is a work of yours to write the electronic configurations of all the elements. So as if you are having a periodic table also, okay, you go through the numbers, or you go through the symbols and then the names of that particular elements and write the electronic configurations on your own. You write at least once or twice such that it becomes very clear. Okay. So there are some disturbances related to that we will explain when we are solving some of the numericals related to that. Okay. We are having then exceptions in case of that. So the exception is, so here in case of this exception, 24 and 29 in case of chromium and then copper. So here there is a set of half filled configuration, it is a completely filled configuration. There is a shifting of an electron from 4s to the 3d. Okay, so just you try on your own the electronic configurations from the atomic number 1 to the atomic number 54. Okay, at least you must be very first perfect with the 36 at least. Then we will have the next set in the form of the 54. That is very easy. In case of the up to I think 4p we are having this 36. Then we have the another 18, I think 18 makes that go to the 54. Okay, so that you have to try on your own. Okay, so this totally completes the theoretical concept with respect to which one? The structure of an atom. Okay, so in the next session we will have the numerical problems or theoretical numerical problems related to the structure of an atom, and in the next further sessions we will move on to the competitive discussions. This means solving of the competitive multiple choice questions related to the NEET or the JEE Mains or maybe the KCET. Okay, so that we will do or that we will work out in the upcoming sessions in the same chapter that is called as the structure of an atom. So thank you very much.